Continuing on with the notes for this lesson, this is day 2. We're going to start with the converse of the isosceles triangle theorem. This is basically just the opposite of what we said before. So now, if we have two angles that are congruent, then the sides opposite those angles are congruent. So basically says if you start with two angles congruent, those are base angles. And if you have base angles congruent, you'll have legs congruent. So in this picture, we'd have AC congruent to AB, which is helpful because the example here says, well, AC is 12. And if AC is 12 and we want the length of AB, those are the legs that are congruent. AB would have to be 12 also. It's just another way to know that you have isosceles triangles. So rather than two congruent sides, you could also know it from two congruent angles. So now we want true or false questions here. I want to know, is AB congruent to segment CB? Are they the same length? One of the issues with this problem here, this picture, there's a lot in this picture. You need to basically ignore some of it. We need to ignore everything that's not this outer angle, this outer triangle. Because if we're wanting AB and CB, you don't need segment D at all. Point D. You don't need point E. We're going to ignore everything that's not including that triangle. And in that triangle, we happen to have angle A congruent to angle C, which is what we just talked about in that theorem. If you have base angles congruent, you could jump to saying that you have legs congruent. That is a true statement. Since AB and segment CB in the triangle are congruent, and ABC has two congruent base angles, A and C, then yes, segment AB is congruent to segment CB. That's what I just said. I just wrote it out. So if you need to pause it, you can look that up. So the next question is from the same picture originally, but now it's just talking about angle A and angle DEA. And if you're looking at angle A and angle DEA, it's not using that whole triangle. It's not using ABC. It's just looking in triangle and ADE. And originally in that triangle, you had marked that segment AD is congruent to segment DE, meaning originally in that triangle, it was marked as isosceles. If you have an isosceles triangle, the base angles will be congruent. So I just wrote out, since angle A and angle DEA are in triangle ADE, the little guy, and that triangle has two congruent segments, those legs, AD and DE, then yes, the base angles are congruent. Yes, angle A is congruent to angle DEA. There's more properties we can get with isosceles triangles, and it has to do with that vertex angle. It says if a line or a segment or a ray bisects the vertex angle, remember the vertex angle is the angle where those two legs are intersecting, so C. If we take C and bisect it, we cut it into two congruent segments. If this happens in an isosceles triangle, then the line is also the perpendicular bisector of the base. So what that means, if in a picture you would have angle ACD, so we had the whole angle C, and now we just bisect it into ACD, if it's congruent to the one on the other side, BCD, if we bisect the angle, then that line is the perpendicular bisector, meaning AD would be equal to DB. We know D is the midpoint. We bisected it. We chopped it in half. And it's perpendicular. So, and we would know, well, there's my chopping it in half. Now they're equal. But we'd also know that angle CDB is a right angle. We are perpendicular to the base. So again, that means if you start out with just saying, oh, hey, look, those angles at the top are equal. They were bisected. Then you will know that those are also equal. They were cut in half, and you end up with a right angle. You can use it for problems like example 9 here. So in this problem, we're told it's an isosceles triangle. They start out saying AT is congruent to TH. They also say that ATM is congruent to HTM. So when we know that, so I'm marking my picture, we're knowing that it's a isosceles triangle. We also were told that those top angles there, I put an X because it's hard to sketch that in, but it's basically saying they're congruent. We had one whole angle, but now we have two equal angles. That's what we just said is the scenario. We bisected the angle. I'm supposed to find the value of X and the length of segment AH. So because we bisected that angle, we get to know that we were the perpendicular bisector to the base. So we know for sure that there's a right angle down there. And if there's a right angle there, there's one on the other side. So we have a triangle. If you look at triangle ATM, you have a triangle where you know two of your three angles. So we can add them up and set them equal to 180. Combining 54 and 90 gets you 144. Subtracting it from 180 gets you 36 degrees. So we've found the value of X just because we were using the perpendicular part of it. But we never used the bisector part of it. We had originally, before that line TM was drawn in, we had segment AH. That's what I'm ultimately looking for here. And in that, as soon as you draw in this bisector, it's perpendicular like we just said, but it bisected, meaning if 5 is segment AM, then 5 is segment MH. And apparently I didn't even put that in there. And if 5 is segment MH, then we can know that AH would be 5 plus 5. Segment addition postulate would tell us that that would be a total of 10. Next example, in an isosceles triangle, angle A is the vertex angle. B and C are base angles. I want to know which sides would be congruent. I would definitely draw a picture for this. It will help a lot. So I made 2 sides congruent, but we made A the vertex angle, which means A has to be the angle where those 2 congruent sides meet. B and C would be the angles that would be congruent, the ones opposite your congruent sides. So we would just say what we just wrote in, that AB and AC are congruent. Then, if I told you angle A is 100 degrees, meaning if my picture was horribly not to scale, which it definitely is not to scale, what would we know about CB? So CB would have to be the longest segment. And that's related to when we talked about hypotenuses are across from the right angles and the congruent angles are across from the sides that are equal. It's related to the fact that if you have a 100-degree angle in the picture, there's not going to be any other angle in this picture bigger than that. Those angles would have to be smaller in order to still add up to 180 as a triangle. You can only have one obtuse angle in a triangle. So if this angle is 100, that means that the side across from it will have to be the longest side in the triangle. So it's related to the fact like a hypotenuse is always the longest side in your right triangle because the 90 degrees is the biggest angle in that triangle. Now specifically, if we know that angle is 100 degrees, we can find B and C. And that's because B and C are base angles, and base angles have to be congruent. So if you call one of them X, we're going to call the other one X. And if you add up 100x and x, you can combine your like terms and end up solving. I'm going to subtract 100 and divide by 2. And that means that those 2 angles are both 40 because then they're congruent, and all 3 of them would add up to 180 degrees. Example 11, we are told that the perpendicular bisector of CB is called segment AD. It's not in the picture, but we could draw it in. And the measure of angle A right now at the beginning of this problem is 40 degrees. We're supposed to find out lots of information about this. Now, first of all, if I'm going to classify triangle ABC, that's what we're starting with right now, I see 2 sides are congruent. Anytime 2 sides are congruent, that's an isosceles triangle. But once you draw in segment AD, if you make it the perpendicular bisector, so I'm putting it as a right angle, we now know that ABD, the other triangle they're asking about first here, it's a right triangle. However, it's also the bisector of the base. It's the bisector of segment CB. So if the whole thing used to be 11, we just chopped it in half. We got 5.5. We also could have started talking about angle A being a 40-degree angle, but we bisected that angle with segment AD. And if you bisect a 40-degree angle, you just made 2 20-degree angles. So what I like to do is basically what we just did. Fill out all kinds of crap in this picture, and then let's go answer some questions. Segment CA is right now congruent to segment BA. That was already marked for us. That's how we knew it was isosceles at the beginning. So if I want to find the measure of angle BAD, we just figured out that's 20. And that's because the whole angle was 40 until we bisected it. Bisecting 40 gets us 20. Next, it asks for angle ADB. D would be our vertex here. So ADB is the angle with D at the corner. And we said since that was a perpendicular bisector, that's a 90-degree angle. ADC, again, is another angle with D at the vertex. So that's where the 90-degree angle is. Lastly, it asks, angle ACB is congruent to what other angle? We just want the name here. And if you look at ACB, that's just the angle with C at the vertex. That's a base angle. Base angles are congruent, so basically we're just trying to find out another name for this angle over here. You could call it angle B, or you could use 3 letters and call it ABC. As long as B is either the only letter you used or the second letter, then you named it properly. That's all we're going through. It has a lot of stuff with the properties of isosceles triangles, but make sure you're working on the IXL to 90 points for that, and then there's a practice worksheet that goes along with it too.